asked questions, but this is a very complicated situation. We don't have good solid answers on exactly what can be done to further mitigate this. But right now I know you need to get your homes checked. Okay, enough with the shallow gas. I'll answer your questions at the end. I know there's probably a lot of questions. We've got data, we've got a few answers, a lot of questions I don't have answers to yet. What we're going to talk about next is the sinkhole and how it's changed. Then I'm going to talk about the cavern. I'm going to talk about the collapse zone characterization and stability, and then I'm going to touch a little bit on the path forward on where things go. The area of the sinkhole has grown. It's now about 8 acres. It was 5.5 last time I talked to you. We are still seeing gradual subsidence outside of the sinkhole to the west. The low water that we've had for the last couple of weeks, or last week anyway, allowed us to fairly well define the edges of the sinkhole now, because we've got a couple air photos taken about the time the wind was out of the north and the water was down. The large bubble plume has disappeared. Bruce Martin mentioned that. This may indicate the gas is depleted, but the other thing is may indicate the gas is accumulating in the collapse zone. The sinkhole has had a pattern of burping periodically, where it will burp, the water level will change, a little bit of gas will come out, and then it'll go back to steady. That is an indication that small amounts of gas may be accumulating somewhere in the subsurface, and we can't ignore that. Right now, all I can tell you is time will tell how that's going. The area of maximum subsidence has not changed. This is the circle. You can see we do have some areas. This was taken at fairly low water of subsidence along the pipeline and stuff. I still feel that that area of subsidence is fairly conservative. However, and I'll talk about this in a couple slides, we have retained as a contractor to Shaw, the Itasca group. These are world experts in subsidence, collapse, and all things related to that. They're actually, one of their first tasks is to review this and do a much more sophisticated analysis than I did and see, hopefully confirm that the 1,500-foot diameter is about as big as we think it's going to get, the sinkhole. The sinkhole changes over time. The current capacity is about 660,000 cubic yards. On the 9th of October, it had a shape like this. This was a very sharp point going down to 440 feet. The 30th of October, this was before the last slump, before the bubbles disappeared. You can see the shape here. And this is what it looked like on the 1st, which was the day after this was taken the morning of the slump. This was taken 2 days later. So what's happening is the sinkhole, it's not as deep, but the deeper parts have kind of widened out, and I think you can see it on the next slide. This is how it's changed. The purple line here was the 1st of October, and then the current configuration is the green line here. So you can see how the sinkhole is changing, and when I say this thing is evolving, this is about the best example I can show. The situation's evolving, nothing is steady state. This is just what it is. But these are profiles north, south, and east, west through the sinkhole. I'm going to talk a little bit about cavern stability, Bruce mentioned it. I'm going to show you the hard numbers that basically back up what he's saying. This was an independent analysis of the Texas brine data that Shaw did as part of our task. The data came from Texas brine. We've done the graphs and stuff I'm showing here to basically support what Bruce just said. In the cavern, we still do have unaccounted for volume of voids. The Itasca folks are working on this. It's not missing volume, we just can't account for all the volume. So that we're working on it. We don't know where the volume that is filling the cavern, exactly where it came from. We're working on that. We don't know what the void space in the collapse zone out here look like. We just don't know. And we'll have a better idea once the seismic imaging of the collapse zone is, the data are available. The sinkhole and the collapse zone are changing. We see the cavern filling up. We see the sinkhole changing up here. This is the 1st of October profile, obviously. The thing is changing all the time, and the graphs, some of the graphs I'm going to show will illustrate that. And the big hum, we're fairly comfortable. This is one likely source. We have sampled the crude, the gas, and the brine now, the big hum, and we should have a comparative analysis, I think shortly after Thanksgiving, on the crude from the big hum and the crude we collected out of the cavern. The other thing I want to show, last time I showed that the salt here was gone. The Itasca folks came in and explained to me that Gary Hecox was probably wrong one more time, that they think if any salt spalling occurred during the collapse, it was probably just on the bottom of the overhang. They felt it's probably very unlikely that the entire overhang collapsed. So we put it back in as a to be determined. The seismic profiling that was in Compliance Order 3 will go a long ways towards helping us answer that. This is the top of the salt dome. These are structure contour maps. These are just contours that define the elevation of the salt dome. I'll show you a cross section here in the next slide. But what we've done to better understand this, we have pulled in all of the elevations from the 3D seismic that was run in 2007 and incorporated those into this area of the dome. And that markedly changed the configuration and what the edge of the salt looked like. So we pulled those in. We only got the 3D seismic for this area. They did shoot the whole dome, but we only got it for this, so that's what we updated, and that's where we're working. This is a cross-section, 1-to-1, no vertical exaggeration. This is the salt dome here. Cap rock is in green. The bottom of the alluvial aquifer is just above the cap rock. The top of the aquifer is here. The ground surface is up here. So this is 1-to-1. This is not a cartoon. This is based on real geologic maps and data. So this is just putting all the data together. It's in 3D, but I'm showing you a 2D cross-section because sometimes 3D gets a little confusing. Here's the big hum. This is from the structure contour map from an oil and gas zone that was developed out in this area. You can see how the big hum comes in. And here's the cavern with part of it filled and part of it still full of brine. So in cross-section, you're looking north, and you would be at about an elevation of about minus 6,000 feet looking at this if you were down on the ground. So that's what you're looking at. I wanted to show you that so you have an idea when we talk about this stuff, just how everything fits together. Okay, going on to the cavern. We get a lot of data now out of the Texas Brine collects. We get it every day. We're analyzing it. This is the volume of gas flared out of the cavern. Again, the same type of curve. You saw a lot at the early on when they started flaring, and now it's more or less flattened out.